One of the application of exponential function is interest compounding. Let me give you an example. Suppose you're investing P dollars. You're investing P dollars and for an infinite time period. Okay, and initially you start with time period say t equals to 0, and r is the interest rate. Well, what you are also doing is this, that this interest rate is compounded n times a year. Okay, it could be weekly, it could be monthly, it could be daily, it could be anything. Okay, so supposedly if it is added at regular intervals n times a year, n is the number of compounding periods in a year. Okay, a specific example is, suppose that you're investing $100 at 10% rate with the compounding of 12. Okay, so it will be added 12 times a year. So after 1 month, how much you will have? You have invested $100. Okay, let me just give you here. You have invested $100 plus you will be getting the 10% interest on this on this $100 annually, but which is going to be divided among 12 compounding periods. Okay, so it is 10% of $100 is 10, which is divided by 12, and which is going to be 0.833. So 100 plus 0.833 is 100.833. After 2 months, what will you have? You will have this much amount in your bank account after 1 month. So at the end of the second period, at the end of the second compounding period, your amount would have increased from 100. You started with 100, it went to 100.833, and then you'll be given interest on this 100.833. So your interest is being added and you're getting interest on interest. Are you getting the point? You're getting interest on interest. So 0.833 is the interest which you gathered in the first period, but you're also getting interest on this interest. So it is 100.833 plus 10% of 100.833 upon 12. So it is 100.833 plus 10.0833 divided by 12, and this is going to be 101.673 and so on. Okay, let us do this algebraically. Suppose n is the compounding period. So after, and you have invested say P dollars, rate of interest is R, n is the number of compounding periods which you have. So after the first compounding period, how much you will have? You will have initially the amount of P which you have invested, plus you will have rate of, see, you will have P plus the amount of interest which you will have on this P divided by the number of period. Okay, so I can write this as P into 1 plus R by N. Now for the second compounding period, this is the amount which you have in the bank account. So you will have initially, you will have this much in your bank account, plus you will be getting interest on this amount, which is P into 1 plus R by N divided by the number of compounding periods, and you will have this P into 1 plus R by N plus R by N into P into 1 plus R by N. So you can take a 1 plus R by N common and you will have this. So it is after 2 periods you will have eventually P into 1 plus R by N square. Getting? In the third period, how much you will have? You will have the amount of P into 1 plus R by N square in your account. You will be getting interest on this amount. You'll be getting interest on this amount divided by the number of compounding periods. So you will eventually have P into 1 plus R by N cube, and so on. So after n compounding periods in a year, you will have this much amount in, that is P into 1 plus R by N to the power N. So after first period, when n is equal to 1, you have, after first compounding period in a year, you have the amount P into 1 plus R by N to the power 1. After second compounding period in a year, you'll have the amount P into 1 plus R by N to the power 2. After n compounding periods in a year, you'll have P into 1 plus R by N to the power N. That is 1 year. After two n compounding periods, that is n compounding periods are in particular year, in 1 year. 2n compounding periods will be for 2 years. So the amount which you will have is p into 1 plus r by n to the power 2n. And after tn compounding periods, that will be for t years, it will be p into 1 plus r by n to the power tn. Okay, so after t periods, after t years with n compounding periods each year, the amount which you will have is p into 1 plus r by n to the power tn. So you have invested p dollars. The rate of interest is r% per annum. Compounding periods are n compounding periods in a year. You've invested this for t years. So the amount which you will have is p into 1 plus r by n to the power tn. Okay, and you yourself have derived this, that this is the way you will find out the total amount in your bank account. Now, in case if you have a continuous compounding, this is sort of a discrete compounding case. Suppose you have continuous compounding, then this is the amount which you have. Now, n, this should be n. Okay, so n, there are continuous periods, okay, continuous compounding periods. So you will have n is going to infinity. So it is, you will be putting a limit of n tends to infinity. You will put the limit here. P is going to come out of the limit, it being constant. So it is 1 plus r by n to the power n by r to the power rt. Okay, but before than that, how do you actually get this? Okay, you started up with a formula. P into 1 plus r by n to the power tn. Can I write this as 1 plus r by n? Okay, then the reciprocal of this, which is n by r into tn, into rt. Okay, so n by r into rt will be only nt. n by r into rt is nt. You've just divided and multiplied this nt terms by r. Okay, and why you have done this is because you know this, that limit of x tends to 0 when x is tending towards infinity. 1 plus 1 upon x to the power x is e. This is the this is one of the result of differential calculus, which is, and here x is n by r, so 1 upon x is r by n. X is 1 by r, so 1 upon x is r by n, and this is your x. So what you will have eventually here is that limit of n tends to infinity. This and this expression, once you put n tends to infinity, this will go to e. Actually, it should be n by r going to infinity. Okay, it should be n by r going to infinity. So this is equal to e. So what you will have is p into e to the power rt. This expression has become e, so it is p into e to the power rt. So this is the amount, and this is one of the application of the exponential function.